Good afternoon, everybody. We're back here with another presentation at the RSN Spring Conferences presented by WPI. I'm Francis O'Rourke. I'm your host here. Joining me right now to talk about FRC Vision on Raspberry Pis and using desktop simulation of robot code is Peter Johnson. Peter, why don't you tell us all a little bit about yourself?
Sure. Yeah, I've been volunteering with FIRST since about 2008 is when I got involved. Actually, summer 2007. Started as a mentor on 294, and gradually got involved with the control system side of things. Roughly around, actually very early on, because the C Rio came out in 2009. So I was involved with a couple of folks, including Joe Ross on 330, doing beta testing on that, and
Oh,
then got much more involved. When we got into the Robo Rio era. So I was involved. 294 was one of the teams selected to be an alpha test for the first iteration of the Robo Rio. And then I was involved in alpha testing and beta testing. And then circa around 2016 or so, 2015, 2016, I got much more involved with the true library development. So on WPILib and so over the years, over the last few years, I started out with a rewrite of network tables. So I wrote the implementation for that that's used for C++ and Java. And then a year after that, wrote camera server. So how we do all of
oh,
the camera streaming for USB cameras is all done. It's all code that I wrote as part of that. And then more recently, I've done FRC Vision image, and then but of course the robot simulation, the user interface for that. So a couple of those things we'll go through today. But that's kind of been my background. I retired from 294 mentoring a couple of years ago, but so now I'm just doing volunteer work for WPILib, and I do volunteer at events as a CSA, CSA to champs on Einstein
wow.
once, and so really had a lot of fun switching more into the volunteer role.
That's great. Well, thank you, Peter. So we're going to get into the presentation in just a quick second,
Sure.
but before we begin, I want to just again thank you for being here, Peter, and also thank the groups that can make this possible. And that one of those is WPI. Of course, WPI stands for Worcester Polytechnic Institute. They're a leader in project-based education, and they were the first university to offer not just a BS, but also an MS and a PhD in robotics engineering. So if you like robots, or if you're interested in becoming a student, or maybe sponsoring one of those projects that the WPI is well known for, just visit wpi.edu for lots more information. But with all that being said, Peter, we'll go ahead and take it away and let us know all about FRC Vision using the Raspberry Pi.
Sure. Yeah. So I'll start with talking about FRC Vision, and the way I'll kick off is first why use a coprocessor at all. The Robo Rio has a lot of capability, so why is a coprocessor valuable? I do have a few charts on kind of primary introduction to networking. I'm going to skip over those in the interest of time, but they are going to be in the chart deck for reference. Talk a little bit about what FRC Vision is and how to get started with it, and then I'll do a quick little demo of doing some stuff with FRC Vision. So let's start out by talking about what is a coprocessor. So your robot code, when you typically write your C++, Java, or LabVIEW robot code, that runs on the Robo Rio. So that's the main robot processor. Now, a coprocessor is an additional independent processor on the robot. So it could be as much as a laptop. In fact, there's been a few teams over the years who have actually used laptops as coprocessors. But more typically, a coprocessor is going to be an inexpensive, lightweight, single board computer. Some examples of this.
Oh, hey everybody! Sorry about that. We have
So,
a oh,
sure.
hey Peter, you there?
Yes. Yep. I'm here.
Okay, great. We had a little bit of a freeze on your end there, really quick.
Oh,
Can
okay.
you just repeat that what you said in that last slide for everybody?
Oh, sure. Yeah. So should I start from the top?
Yes, please.
Okay. Um, your robot code runs on the Robo Rio, so that's the main robot processor. And a coprocessor is going to be an additional independent processor on the robot. So that could be a laptop. And a few teams over the years have used laptops. But more typically, a coprocessor is an inexpensive, lightweight single board computer. Some examples of this are the Raspberry Pi, which of course is going to be the focus of our presentation here, because that's what FRC Vision is for. The Odroid, NVIDIA Jetson, like the TK1, TX2, or Nano are other examples. Now, the coprocessor needs a way to communicate with the RoboRio because it's running separately from your robot code. Typically we use coprocessors for vision processing. So you might want to send vision target info from the coprocessor to the RoboRio. And often you need to have the coprocessor communicate with the driver station as well. So an example of this would be camera streaming, for example. So most commonly what we do is use network tables over Ethernet, and that's kind of the standard approach for communicating pieces of data around the robot network. So that's standard, and I would definitely recommend using that. And then for the camera streaming piece, so the standard WPILib provided approach is what's called MJPEG, so motion JPEG over HTTP, but other third-party options exist, H.264 over RTSP. There's several other ones out there. We're looking at enhancing WPILib with some of those features, but right now the standard approach is that first one and what's bundled with the image. So going on, we can talk about why would you want to use a coprocessor for vision? Well, since the RoboRio can do camera streaming and vision processing, why is it beneficial to do stuff on a coprocessor? So the first and foremost thing is that the separation of concerns improves reliability. And separation of concerns is a term out of engineering, and it means doing separate things separately on separate pieces of physical devices. And so while cameras and vision are clearly very valuable for autonomous and oftentimes beneficial for teleoperated mode, they typically, almost always, are not required for successful robot operation. You can still drive the robot around, score points, even without vision. You might not be as reliable or successful without it, but it certainly is not required to drive the robot. And so if you write your RoboRio robot code to successfully operate without the cameras or vision, you can take greater risks in the vision implementation. As an example with that is using a coprocessor, which has separate power supply, so it might have some reliability there. Or you may want to try a different language. Your robot code is written in Java. Well, maybe you want to try using Python for image processing. So that's easy to do on a coprocessor without impacting the reliability of your robot code. So the other thing that the advantage of the coprocessor is that if you put vision on a completely separate processor, that means that any issues with that code, whether it be memory usage, high CPU, other bugs, even the entire processor losing power, won't crash your robot program. The vision processing stops running, your robot program keeps running, you can still drive the robot. And using network tables kind of facilitates this because network tables provides methods to every time you call a get function to get information from network tables, you provide a default. And so you can provide nice, safe defaults so that your robot code, when it's looking for that vision processing target, you can just have a default value of like, oh, I didn't find a vision processing target, so keep running. So it's pretty easy to do the kind of second part of this, which is to keep your robot code running. And so then you can take a little bit more risk on the coprocessor side of things. The biggest advantage of using a coprocessor is it's faster processing. A Raspberry Pi 3 is, roughly speaking, is about twice the processing power of a RoboRio. A Raspberry Pi 4 is twice of that. It's twice the processing power of the Raspberry Pi 3. So it's approximately 4 times faster than a Rio. And why is that helpful? It gives you, it takes less time to process a frame, which reduces latency. You can run at higher frames per second and get more faster and more precise control of your robot from the vision inputs if you can run it on a faster processor.
Hey, Peter, can I ask really quickly, just a real quick
Sure.
question? So I'm a neophyte when it comes to programming, especially with vision processing. But if you say that the Raspberry Pi 4 runs 4 times faster than the RoboRio,
Mhm.
Why don't we do everything on the Raspberry Pi 4?
So there's actually teams that have been looking at doing that,
Oh,
or running almost everything on a Raspberry Pi or on a Jetson, for example. The main reason we have to use a RoboRio is all the safety controls are on the
uh,
RoboRio. So the RoboRio has software running on it called Netcom, which connects the driver station to the robot, and that's what your robot program talks to is Netcom. And there's also a piece of logic called an FPGA on the RoboRio that makes sure everything is disabled. So all the PWMs disable, all the relays disable, and then also make sure that the CAN bus stuff turns off as well.
okay.
So all the safety controls are on the RoboRio, and that's why we can't solely go to the Raspberry Pi. I think the other reason to not use a Raspberry Pi for everything is again the separation of concerns. I mean, a Raspberry Pi is definitely not as robust as the RoboRio.
Yeah.
I mean, a RoboRio you can drop it, you can hit 12 volts on any pin. I mean, and it lives. I mean, it's really hard to kill a RoboRio, and so that's the main benefit of still keeping your robot program running on the RoboRio is that way you don't have to worry about dying on you due to short circuit or something like that.
Oh, that's great.
So it's super reliable.
And just a note as well. If
Mhm.
anybody in the chat has a question, don't forget you can submit those questions to us, and we'll ask Peter toward the end of the presentation. Just type !Q and your question in chat, and we'll record them
Yeah,
and send them off to Peter as well. So thank you, Peter,
yeah,
for answering
happy
that.
to answer.
Go
Yep.
ahead. Go ahead. Sorry for interrupting. Go
Yeah.
ahead and continue.
No, no, no. Thank you. So the other reason you can use a other kind of benefit of using a coprocessor, and part of what we'll talk about today, is it enables easy experimentation. So many of you are at home right now. I think almost all of us are, and you probably don't have access to a robot. But on the other hand, it's pretty easy to get a Raspberry Pi. So this is a way that you can develop vision programs, get that experience. All you need is a USB camera and a Raspberry Pi, and you can be off to the races. USB cameras are a little bit harder to find right now, but certainly Raspberry Pi you should be able to get that easily. So and just in general during a season, this means that you don't need access to the robot to continue working on your vision program. So I'll skip over these charts. Basically, I just wanted to, when you add a coprocessor to the system, it's much more important to understand how networking works on the RoboRio and the robot network in general. So I have some charts in here. We'll make sure that we share those charts later. There's certainly a lot of information on the FRC docs website. So all the WPILib documentation. There's a whole section on networking in there, and I highly encourage you, if you're looking at using a coprocessor on your robot, to make sure to read up on that. There's a lot of kind of interesting aspects that you have to learn or are good to learn about how addresses are automatically assigned or statically assigned, and some of the pros and cons of those different aspects. So I'll just flip through these real quickly. It's not super important until you start working on the robot with the coprocessor. So I will talk briefly though about network connections with the coprocessor. So again, all of these things are hooked up through Ethernet or the driver station on the other side of a wireless link. So you have the RoboRio, so that's the robot program where the robot program is running. It's running a network table server, and that's what your driver station dashboard application connects to every time you write a smart dashboard value or something along those lines. Typically, dashboard apps are things like Shuffleboard or Smart Dashboard or the LabVIEW dashboard. So those connect to the network table server to get information. And the coprocessor is running separately, of course. It's a separate processor. Your Vision program is running on that, and it's running also a network tables client. And so the one of the most important things for the coprocessor to do is to connect to the network table server on the RoboRio. So it has to go and establish that connection. And the type of information going over that connection are going to be the any sort of vision target information, but it's also how the vision program informs the dashboard of where to find the camera streams. So that information is published through network tables. And so the dashboard application is going to get that camera stream info from network tables and then establish a separate connection to a camera server running on the vision processor. So this is an example of when you've got a coprocessor and a RoboRio. But of course, for testing purposes, um, you may not have a RoboRio. So that's what this chart shows. Is it shows the coprocessor without a RoboRio. You can actually have the coprocessor run as a network table server. There's a very simple switch I'll show in the demo here on the FRC Vision to flip it over to a server mode, and then you can set up the dashboard application to connect just to the coprocessor. So you don't need a RoboRio at all. You can get camera streams, you can run the Vision program, you can get the results of the Vision program, all without a RoboRio on the network. So let's talk a little bit about FRC Vision. So what is FRC Vision? So FRC Vision is an image for the Raspberry Pi. It really works on any of them. It will work on the 2, it'll work on the 3, it'll work on the 4. I would definitely recommend for vision processing using at least a 3. The 4 is only like $10 more expensive. So if you don't have a Raspberry Pi 3 sitting on a shelf and you're just looking to buy something, I would definitely recommend going off and getting a 4. And this is and the image is designed for use as a robot coprocessor. It's explicitly for the purposes of vision and camera streaming. So it uses the Raspberry distribution. That's what it's based on. So all of the standard Raspberry Pi packages can be installed. So it makes it really easy to add additional things. If the image doesn't include something, you can always add more to it. It's headless. What this means is that there's no GUI, there's no Windows, there's no X Windows running on the Pi. You can still hook up a display. You can still hook up an HDMI cable to the Pi and a keyboard, but you're just going to get a console. Now, the reason we did this in the image is all that stuff is overhead, and it adds to how long things take to boot. So we wanted it to really free up as many resources as possible to run your Vision application and also make it so it boots as quickly as possible. So the easiest way to do this was to not have a GUI installed. The other nice thing about FRC Vision is it is legal for competition out of the box. So we explicitly disabled all of the wireless functionality in the Pi. So that includes both Wi-Fi and Bluetooth, because that's not legal for competition. So we went ahead and disabled that for you. It is possible to re-enable it, but we kind of recommend not doing it and just using the Pi. The other thing we did in the image is it has a read-only file system. Most Pis, if you just use the standard Pi distribution, it when it boots up, the file system is writable. And as we know, the robot gets powered off all the time without warning, oftentimes. I mean, either when you're powering it off at the end of the match, during testing, all the time, everyone hits a power switch. So typically, operating systems don't really like that. They don't like being switched off when the file system is writable. And so by going to a read-only file system, by default, it makes it so that it's robust against hard power-offs. We do have some nice automation in terms of switches to turn this off and on the web dashboard to make it writable, switch it back to read-only. But this is one of the few images out there that defaults to read-only by default. So that's one really nice feature.
So really quick, Peter, if it's read-only, what kind of logging or like data storage do you have with this Vision? Is it sent to the RoboRio or?
Yeah, so the idea is that it's sent to the RoboRio. So you basically anything that you care about, you should publish to network tables, and not write locally to the Pi. Yep.
Great.
Yeah, so it boots up in less than 20 seconds, so that's really nice. So that's from power applied to Vision program running. So it's definitely going to be up before the radio when you turn the robot on. It's most likely going to be up before the RoboRio as well. So it's very fast to start up. The other really nice thing about this is that the image includes a full copy of WPILib, both C++ and Java, as well as all the Robot Pi Python libraries. And it includes everything you would typically have on a robot. So it has OpenCV, it has camera server, it has network tables. It actually has the entirety of WPILib. Of course, you can't directly control a PWM. The Raspberry Pi doesn't have PWM outputs, but pretty much your robot, you can literally copy a robot program to this and a Java robot program, it'll just run out of the box. So we have some example programs, which we'll talk about in a minute, to use as a basis. You don't really want to use what the robot program is. You want to do something more intended for vision. So we do have some starting applications to get started that way. The FRC Vision also includes a web dashboard. So this is useful for configuring the Pi, like setting network settings, monitoring the Vision program. So it does have a little web console, so you can get console output out of your program. If your Vision program is printing stuff to the display, you can get that interactively from the web dashboard. You can change camera and network settings, and you can upload applications. And as I mentioned, there's several example programs provided to use as a basis for vision processing code. So to get started, really all you need is a Raspberry Pi 3 or 4 with a power adapter, and then a micro SD card. I would recommend at least 8 GB. You don't need to get something ridiculously huge, like 128 gig. 8 GB is plenty. And typically you'll find, if you look online, there's often bundles that are sold. So it like comes with a Pi 3 or 4, a power adapter, and an SD card. You're also going to need a SD card reader for your computer. Um, Many computers have ones integrated, but you can find cheap USB sticks that do this as well. There's like a little USB and you plug in the card. I would actually recommend getting the USB one. Sometimes the integrated ones are a little flaky or really slow. So the USB one is like $20. It's an investment that I think is well worth it. You'll need the FRC Vision image, so that's on GitHub, and the link's there. And you'll need a program to write the image to the card. I recommend Belina Etcher. It's very commonly used out there for writing Pi images. It's available for multiple platforms: Mac, Windows, and Linux. So that's an easy way to write the image to the card. And optionally, this is mainly useful if problems occur. Is getting a USB keyboard and an HDMI monitor. Not required, but can be helpful if you run into problems. So the initial steps here, and I won't demo this because it's really is pretty straightforward. Is You use Belina Etcher to write the image to the card. You put the card into the Pi, and you connect the Pi to the home network with Ethernet. So it is possible to connect just point to point directly to your computer, but I would kind of recommend when you're first getting started to connect it to the home network. It's a little bit more robust when first getting started. Then connect power to the Pi. The first boot up takes a little bit longer. 40 seconds to a minute is common. Depends on how big the SD card is. What's actually happening here is it resizes the image to take up the entirety of the SD card. So it takes a little bit longer the first boot. And then you open up a web browser to frcvision.local. And if the page appears, you're connected. So I'll actually start there. There's a couple of charts in here talking about setting up a USB camera and customizing the Java example and seeing network tables vision output. But I'm actually going to demo that live because I think that's a little bit more interesting than just going through a chart.
Oh, I like that too.
So hopefully you guys can still see my desktop. And what I'll do is pull up the web browser here.
Okay.
And go to frcvision.local. And so this is the FRC Vision webpage. So what I've got here at home is I've got the Raspberry Pi just hooked up to my home network, and of course my laptop's on the home network as well. So this is the main page for FRC Vision. So it shows some system status here. You can reboot the system here as well. CPU utilization, network utilization, what the CPU temperature is. This happens to be a Raspberry Pi 4 or 4 GB, so it has tons and tons of memory, not much in use. And then there's several tabs along the left. So there's a Vision status tab. So the Vision program is set up to run in the background automatically on startup. So this is where you can, I want to disable it for a little bit, want to test some stuff manually on the Pi. This is also where you enable the console output. So by default, it's disabled, but you can enable it. And as you can see, there is a Vision program running. The messages here are saying that it's trying to connect to network tables, and it can't because I don't have a RoboRio at home at the moment either. So at least not on the network. Network settings. So this is where you can set it up to DHCP or static addresses. And then the main tabs here that are most commonly used are the Vision settings and the application tab. So under Vision settings, there's a setting for network tables. So you can set it up as either a client or a server, and you specify your team number if you got it in client mode. And this is also where you set up USB cameras. So in this case, I actually have a camera already connected, which is the Pi internal camera, but I also plugged in a USB camera. So what I'm going to do is add that. So I go down here to add connected camera, and it's going to pop up a big list of cameras. And this lists basically everything that's connected that it can see through Linux. One thing that's a little confusing right now in the image, and I'm looking to figure out a way to fix this, is USB cameras actually appear twice. And I think it has to do with the Linux driver layer. So that's something I'm going to be fixing. There's actually, for every camera, there's actually 3 different addresses which appear. There's just dev video 1 through N, and so there's 1, 2, 3, 4, etc. So that's just Linux just enumerating the cameras. When it starts up, it says, oh, this one's the first one, this one's the second one, etc. Where this is important is if you have multiple USB cameras or have different cameras that you have hooked up, so you want to have a camera looking forward and a camera looking backward on your robot, sometimes those can switch. So the other options, the by ID and by path options, are ways to disambiguate cameras that are when you have multiple cameras. So by ID does it by the make and model of the camera. So say you have a Microsoft LifeCam and a Logitech camera. You can use the by ID to tell the difference between them. The by path is basically the physical port it's plugged into. So if you have it plugged into a USB hub, or the Pi has 4 USB ports, you can actually tell the difference between different USB cameras by what port it's plugged into. So that's a way when you're using multiple cameras to take care of that. So in this case, I'm just going to pick the dev video 1.
Hey, Peter, real quick while we're
Yeah,
here,
sure.
do you have any suggestions on what kind of USB camera a team should use?
So I not directly. I think there's a lot of good options out there. I mean, even those $20 cameras can be pretty effective. I think there are some pros and cons in terms of what has some USB cameras offer higher frame rates, some offer higher resolutions. Really, for first, we really are looking for those cameras with the higher frame rates, lower latency. Some of the HD cameras are actually really good. Some of the Logitech higher end cameras are quite nice. Where you're spending, instead of $20, you spend $50. But they're still fairly inexpensive. Sometimes the best way to do it is just buy like a couple of different ones and test them out and see which work for you.
Cool.
One of the important things that you have camera name, so I'll just call it USB camera. This also is a place where you can change the path if you like. Oh, I added this video 1, but maybe I do want it to be a certain USB port. I can do it here. And really, all the other settings you don't have to set, at least when you're first hooking up a camera. These are really here so that if you want to force a particular resolution or pixel format, or set the brightness or exposure, these are some of the settings that are available. So when I'm initially getting started here, I don't actually have to set any of this stuff up. I can just use the defaults and leave them all blank. Now you'll notice that the save button is disabled. I can't actually click it. So to write to it, because how this is saved is as a configuration file on the Pi itself, I'm going to go up here to the top and click the writable button. And so that makes it writable. And now I can click save. And so this now saves the information about the cameras to a JSON file on the file system. And in about 5 seconds, because it has to reboot the camera process. So your vision processing is running as a separate application than what this web dashboard has gone through. So it needs to go and reset the program. But now I can go and open that stream. So now I've got a camera set up. It default to the lowest possible resolution. So this one's a pretty low res camera. And this is actually a live camera feed. So I can actually stick my hand out. It's just sitting on my desk and wave upside down at the camera feed. So now I have a live camera view, all set up on the Pi, and it's literally that easy with FRC Vision. Now the next thing I can do is I can have it talk to a dashboard. So I've got Shuffleboard running locally. Again, I don't have a RoboRio running locally, but what I can do is I can switch the FRC Vision into server mode. So I'm going to switch it, turn client off, so it runs as a server, and I'll hit save here, and I'll go over to Shuffleboard, which I have running locally, and I can set, and basically right now it's configured to hook up to the robot, But what I can do is go over to the network tables and under preferences and change the server. So oftentimes you'll see a team number here or RoboRio, your team number .local. But what I can do here is I can just say FRC Vision .local. And when I hit OK, it's actually going to connect to the Raspberry Pi instead of the robot. And if I go to the camera server tab here, you'll actually see the two cameras I have on the Pi. So I can go and drag that USB camera over, and I've got a
Ah,
live view on shuffleboard with no robot of that camera. So I'm up and running with that live feed, and that's how you get kind of the initial camera stream working on the Raspberry Pi. Um, the other thing we can do is you probably want to, okay, great, I've got a camera streaming. Now I probably want to do some image processing. So, so on the application tab back on the web page, there are some example programs here. So, so we provided Java, C++, and Python examples, and we can just download that. So, so it just provides a zip file, and what I can do is go and open that up, and what's there is a Java program that uses Gradle to build. Now I already extracted it in a sister folder, so just give me 1 second here. Extract that, and so so under here, it's kind of set up as a normal Gradle application, Gradle Java application, and there is a Java file here. And go ahead and just open this. And the Java file has, there's a lot of stuff in it, but the most important piece is actually down here, pretty close to the end, um, called example pipeline. And what this pipeline lets you do is you could use grep to generate a pipeline, but really you stick your OpenCV and network tables code in here, and then you just save the file, and then you can use Gradle to build. So that is up at this top level. You open a command prompt. I won't demo it live because we're a little time limited, but you run Gradle W build, and what that does is it goes and builds the Java application and puts the result into build libs. And so there's a file here called Java multi-camera server -all. And what we do is back on the web page is go and go down to uploaded Java jar, and we browse for that file. So I've already kind of done this before. So I'm already in that folder, but normally you browse the folder, select the -all jar file, and you, again, it has to be writable, but you can say upload and save. And now the application is successfully uploaded, and now it's actually running that Java application. Anything that you had changed in that Java file is now running on the Raspberry Pi. So so the console output would be appearing here. All the vision settings would still work, and if you open stream, it actually connect to your vision application. So that's how it currently works to upload applications. It's definitely a little bit more manual than how robots work, where you can just say deploy in VS Code. One of the areas that we're working on is actually making that much more integrated. So
oh,
so using Visual Studio Code, having Gradle Rio, kind of the setup in a very similar way, so you can actually develop Raspberry Pi applications the same way you develop your robot application, and do deployment the same sort of way as well through VS Code. So that's still a work in progress. So right now, this is what's available for downloading examples and re-uploading them, but we're working on a more improved workflow for that. So that's kind of the next step.
great. And not to put a, not to put you under pressure, I guess. Is this looking for deployment like in next season, 2021, or?
Yeah, that's right.
Okay.
That's our target for it, is having that available probably later this and the release cycle of FRC Vision is not directly linked to that of WPILib, so so we can actually do a release, and it has that feature in it.
Oh,
So
cool.
yep. All right. So I think that pretty much wraps up FRC Vision. So I'll switch over and quick demo of robot simulation top.
Okay.
Um, and so I'll just show this one chart. Basically the features of the simulation is that, no, let me switch to presentation. Easier.
There we go.
Is a bit easier to see. So first and foremost, there's a GUI for interactive use, and that's mainly what I'll be so what this lets you do is you can change any Rio input. So anything that the Rio is hooked up to the Rio, like an analog input, a gyro. We have things for gyros, all that sort of thing. You can change the input just by typing, and you can see all the RoboRio outputs. So you can see, oh, the PWM is doing this. I'm driving this digital output. It does work for both C++ and Java, and actually Robot Pi is using it now as well. For C++, you do need to, because it needs to build your C++ application for Windows, if you're on Windows, you do need Visual Studio 2018 installed. You can use the free community version is fine, but you do need that installed if you're doing C++ on Windows. If you're doing Java, there's no additional dependencies required. It does have full support for WPILib, including the camera server and network tables. So part of the demo I'll show is actually showing that off a little bit. There's some kind of cool features for pausing and single-stepping periodic loops. So your main robot loop, you can actually pause that and then say, oh, I want to change a couple of values, and single step it, see it run the robot loop just once.
Wow.
So it's really useful for debugging. So many people ask about vendor support. Vendors this was new to 2020, so vendor support was lagging a little bit. But even by mid-season, many vendors do support at least some features in simulation. So I'm expecting that to continue to improve as it matures and as teams use it. I think vendors are seeing the value in it too. So it's very encouraging to see the work that the vendors are doing along these lines in terms of supporting CAN bus devices, letting you do stuff in simulation.
Peter, do you know
Yeah.
any vendors offhand that have that are supporting it presently? Like
Yeah, both CTRI and Rev do have.
Oh.
Yep.
Cool. That's good. So you can put like talons in there, or
you can put So if your robot code uses talons, it will show up in the simulation GUI under the devices window.
Okay. So I'm sure we'll see that in a few minutes. So.
Not necessarily all the support there, but a lot of the support is there.
Great.
So the simulation is cross-platform, so you can run it on Windows, you can run it on Linux. You can run it on Mac. The GUI works on Mac, but some support is missing, so USB cameras don't work. Many of the vendors don't support Mac yet because it's a little harder for them to build for Mac. So, but certainly Windows and Linux are fully supported. And kind of the next step here, and I think where we're headed with support on this is really enabling what's called unit testing. So you can do some automated testing of your robot code without needing a robot. So the GUI is really nice for just playing around and testing things. But if you want to do automated testing, the support is also there for it. We just don't have a lot of good documentation. So that's really the next step, is adding documentation for how to do unit testing using the simulation platform.
So what you're saying is that there's a chance that the programmers on my team don't have to complain to me that they don't have a robot to test their code soon?
Well, they probably still will, but can't prevent that from happening. One of the things that typically drives that is ultimately you do need to tune mechanisms, that sort of thing. So that you do need,
right.
You can do some basic work without access to the physical thing in terms of, what does this button press do, what, and that sort of thing. You can do all those sorts of hookups. We are looking at, I know the Robot Pi platform has this, so we're looking at trying to bring some of those features into C++ and Java for doing some basic physics simulations. So you can, say, have an elevator or an arm or drivetrain where you can say, oh, I've got these motors on the drivetrain, I've got these encoders on the drivetrain. If you set the motor output, it actually has a little bit of a physics model behind it to turn that into encoder inputs.
Wow.
Right now, none of that's integrated, but that's kind of where we're headed.
Cool. All right. Well,
so
No, go ahead.
I'll go to a quick demo here. Just for the sake of time, basically what I did is I went ahead and created a robot project. I just used the GearsBot example. So I just created the GearsBot example program here, and I'm looking at the robot container code. So under the WPILib menu, there's a few different options for desktop. So if you just actually search for desktop, there's two options. So the first one is change desktop support enabled setting. There's an option when creating the project as to whether or not to enable desktop support. By default, it's unchecked. For Java, it doesn't matter as much, but for C++, again, the reason it's unchecked by default is because there's an additional dependency. And when you build your robot code, it's going to try to build for desktop as well. So we didn't want teams to run into issues with that. So by default, we disable it. But you can, if you have an existing project, you can go there and go ahead and enable that. So you just click there and it says, oh, should you enable desktop support? You say yes. And then the next step, if you just want to run it, you can either search for desktop or simulate. And there's an option here to simulate robot code on desktop. So you just click that. And it goes and runs Gradle. And in this case, it's a Java program. And then it pops up this question saying, okay, what extensions do you want to run? So the simulation platform allows multiple extensions to be loaded. So this first one here is Halcyon GUI is the GUI extension. So we'll go ahead and enable that and hit OK. And what it's going to go is go and run the robot simulation. And so it pops this GUI, which shows all of the different inputs and outputs of the robot. It also has joystick support, so you don't need a driver station running. It knows how to talk to the system joysticks on multiple platforms. So this works on Linux as well. And you can assign the joysticks. In this case, I have a Logitech joystick hooked up, and you just drag and drop it to wherever you want to assign it. So I want it on joystick 1, or I want that on joystick 0. In this case, the robot program, you can actually see at the bottom of the window here, bottom of the screen here, this is the prints from your program are actually appearing in VS Code. So they're showing up right here. And so when I remap the joystick away from 0, it actually says, oh, I can't see the joystick button. So it's actually running live. So the robot program is currently running. You can see some counters going up here with the FPGA time and the time and timed robot. And to make this a little bit more interesting, I'm going to go ahead and pull up Shuffleboard as well. So I'll move this camera out of the way. And then what I'll do is I'll have this connect to the simulation. So instead of, again, like we changed before, we changed it to say FRC Vision local, I'm just going to point it to localhost. And because that's where the robot program is running. And so here we are. This is all of the smart dashboard elements in the GearsBot example program. And so I can go back to the robot simulation GUI. Of course, this is a little bit easier with multiple screens, but we'll make do for today.
Yeah.
And I can change an analog input. So this is live, and because we don't need to worry about safety, the robot state is a lot easier to control than with the driver station. I can just click teleoperated, and it runs teleoperated mode. I click disabled. There's no enable, disable, all of that sort of complexity.
Now, are you sure you can't put that in the regular driver station? That would make my life easier, at least until I get run over.
Right. Yeah. No. This will not talk to the real robot. So
okay.
You can feel safe on that.
Fine.
And so I can click teleoperated here. So now the robot's in teleoperated mode, and I can actually change the analog input. And as you can see, as I drag the slider, it's changing the elevator potentiometer value. So this is 100% live. So what's happening here is I'm changing the analog input. The robot code is reading that analog input and putting that value out to network tables, and that's showing up on Shuffleboard. So that's 100% live. Similarly, I can change digital inputs, and that's apparently a limit switch. The other nice thing I can do in the simulation GUI is I can rename things. So I can, by right-clicking on an element, so I went ahead and named this elevator pot just so I know what I'm looking at. By default, it doesn't know, so it just names things input and out. Input 1, 2, 3, 4, 5, based on where it's plugged into, the port number it's plugged into. But this does show live. And as I mentioned, we can say you want to change two values at once, like I want to change both the elevator pot and the limit switch at the same time. So I can go over to the timing window here and click pause. And now the robot program has stopped.
Oh.
So the main loop is completely paused. The reason this works is because we use timed robot, which uses a notifier. So is expected to run every 20 milliseconds. Well, we're in simulated mode. The time is simulated. So we can say, oh, the time is whatever we want it to be. And in this case, I just said, oh, stop moving the time. So the robot code thinks that it's just waiting for the next timestamp to occur. And then I can go and edit the, whatever analog input or output I want. And then I can even single step that main loop and just run it once. So it just runs one periodic loop and you can see it changed. So
Wow.
It changed both values at the same time. And to the robot code, it's like both of these things happened at the same time.
So this is a good way to set the inputs to what you want to be and see what your robot does instantaneously during that output.
Yeah, instantaneously during that time.
Okay.
Yep. And similarly, like the joysticks work too. So if I reach over here to my joystick, you can see it driving the PWM outputs. You can see the access values on the joystick. When you press buttons, it highlights the green LEDs here. And these are all actively running. So as you can see, just there was a claw command that just ran because I pressed one of the buttons that controls the claw.
Oh.
So yeah, it's fully operational here, and you can press different buttons to make it do different things on the joystick and test your robot code without a robot attached.
So I was going to say, so is this seems like a great initially at least a great way to validate your operator interface, right? To like make sure that all the buttons you click run the right commands or set all the inputs correctly based on what you're doing.
Yep. So and yeah, without the physics model or doing stuff with physics, it's not quite as useful for testing autonomous quite yet.
Right.
But certainly you can run autonomous code. If you have just things that are timed in autonomous code, it lets you at least test that. We've actually, one of the last features we added in this season's releases is there is actually a 2D field view. So you can open up a 2D field view and you can load an image of your robot, and so you can actually set your robot position through code and get a little bit of simulation that way. So these are the sorts of things we're going to be adding over, is continuing to do enhancements like this. So definitely more developments to expect in the future that way.
So as I look at this tool, I'm trying to think about how I would use it or how my team would use it, right? Could you could use this to like judge? You may not be able to tune like a PID loop because you need the physical representation of it, but you could see like as you change the value of a potentiometer or an encoder or something, you could see if the correct motor starts driving or if the motor's driving in the right direction, or if they're going at a speed that seems reasonable for what's going on. Okay.
Yeah, that's exactly right. So it's like, oh, when I operate the joystick, are the motors going positive or negative? Is that correct for how they're hooked up in the system? You can go to encoders here and change the encoder counts. Set the direction. You can set like here, there's an analog gyro hooked up, so we can change the gyro angle and say, oh, well, now it's reading 180 degrees, and the robot code is reading that as a live. And you don't have to the great thing about this is that all of this is happening at a low level. So your robot code, I mean, this is literally just the straight example GearSpot example program with no changes to it.
Wow.
So you don't have to do anything to your robot program in order to use this. It just works out of the box.
Very cool.
Yeah. So I know we're running short on time. So it does. The one kind of final feature I did want to show is that USB cameras do work as well. So if you have a camera server in your robot code, which again, based on the previous conversation, you probably should not do, but you should just use FRC Vision instead. But you can go ahead and add to your robot program like I'm doing right now, just calling camera server start automatic capture, and then I'll run that again. So I'll just do simulate again after making that change. Go ahead and open up the GUI again. And so now the simulation is running, but more importantly, if I pull up the, get back to the dashboard application here, it now has a USB camera.
Hey.
And so I can drag that over, and now it's using the USB camera on my laptop.
Wow.
So that's So fortunately, I have two USB cameras, so I can actually demonstrate this.
Yes.
But this is so USB cameras do actually work in simulation mode as well, at least on Windows and Linux. Um, so yeah, so that's really the end of the demo. And really, we'll definitely make sure we open up for questions here.
Yeah, I think this is like a really great tool that teams can use to do a lot of cool stuff. I mean, like
Yeah.
instantly in my head, I'm thinking like, man, it would be nice to be able to test if a limit switch is going to stop before I put my robot out there and it breaks itself, right? Even something as simple as that's so
That's
cool.
right.
So we only have time for a couple of quick questions. So if anybody's got any more, just go ahead and type them into the chat with exclamation point Q and your question, and we'll answer them right away. But so we got one question here. This question comes in, and they are asking. So this is more about the camera stuff. How does the Raspberry Pi image and the whole setup differ from something like a Limelight, right? Why would you? What's the concept behind this as opposed to doing like an integrated solution like that?
Yeah, so the big advantage is that I mean clearly a Raspberry Pi is a lot cheaper. So if you particularly if you're just mainly caring about the streaming video, you just want a video stream to see what's going on. Raspberry Pi with the USB camera is a really inexpensive way to do that. Certainly, there's the other reason to use a Raspberry Pi would be if you want to develop your own vision code rather than have that learning experience of developing that yourself, rather than having a more canned solution off the shelf. I think a lot of teams do value that learning experience. And there are actually some team developed solutions out there as well that are starting to add some features that are maybe similar to what the Limelight provides, in kind of a more team developed sort of way. So where it's open source software, you can download it, you can play around with it. It's not quite as off the shelf ready to use, but is certainly a viable vision solution as well.
Cool. I mean, I think again, I'm not the one that programmed our robot, but I'm pretty sure that this is what we used on our robot this year. And I didn't see any issues with it. We got that part running up really quick and going. Just a matter of getting it on the field and testing it in time, which makes me wish we had we'd use the simulation more a little bit. But no, we'll do one last question here, quick coming up. They're asking about how can you go into some more detail on what we'll be able to do and see with the physics simulation for the simulation program you showed us. What exactly is that going to entail, you think?
Yeah, so the basic concept, how it works we're still kind of fleshing this out. This is kind of a summer development project into the fall. So don't know exactly what it's going to look like, but the concept in my head in the way it works in Robot Pi is there's a set of classes and library stuff in WPILib that provide various physics models, motor models, drivetrain models, that sort of thing. And the basic concept is that then in your robot program there will be a function that's only called in simulation. So then you can write into your code. Like, oh, hook up this motor to this sensor with this model in this sort of way. That's one concept. Certainly another concept would be doing it in some sort of more file descriptive sort of way, where you drag and drop things and have a GUI to write a JSON file and load that. I mean, my kind of sense is, the former is maybe allows a little bit more team flexibility and expressiveness and power in terms of hooking things up. So that's kind of the concept of how at least I think it'll be operating is you'll kind of add that sort of physics simulation into a simulation portion of your robot code that's not run on the real robot, only run in simulation, and we'll provide the libraries so you don't have to derive all the physics models yourself.
All right, cool. All right, and last but not least, we're going to do this one really quick question here. This is from someone from the chat, Trevor Knight. They're asking, could you use a Limelight on or with the Raspberry Pi model or system you've developed here? Like, how would those mesh together, sort of?
Yeah, so how those would mesh together? So the Limelight is basically a separate coprocessor in the same sort of way that the FRC Vision image is. I mean, if you have a Limelight at home sitting there, I mean, certainly you can run FRC Vision as a network table server, and then you could set up the Limelight to talk to it. That might be one way to do it. I mean, certainly from a directly interoperating perspective, I mean, they're doing similar functions. So unless you're doing that something like that where it's taking the place of the RoboRio in a test sort of scenario, they're really kind of independent systems. So you might, but on one robot, you could say use the Limelight for doing your vision tracking, and then you're like, oh, I want 3 USB cameras to view different areas of the robot for the drivers to get that information. And okay, let's just throw on a Raspberry Pi with
Right.
FRC Vision and get those camera streams.
Cool. All right. Well, hey, Peter, thank you so much for joining us this afternoon. This was a lot of really cool information. I'm sure I know that's a lot of my team know about it. I'm glad we're bringing this out to more people to get them educated on this kind of cool stuff you all been working on. So
absolutely.
Everybody
Nice to be here.
Yeah, thank you. Stay tuned, everybody. Coming up right away, we're going to have a presentation by Andy Baker from AndyMark, literally the man who put Andy in AndyMark, talking about manipulators and appendages in FRC robots. So be sure to stay tuned, and we'll see you all in just a quick minute. Thanks, guys.
Thank you.